All right, this is Unit 6.4 of AP Calculus, the fundamental theorem of calculus. Now, I posted a video of what the fundamental theorem of calculus is and a proof. It's actually done by someone else, but it's a very good proof. So please watch that one before you watch this video. So we're trying to connect contextual problems with our understandings of rates, amounts, and definite integrals and accumulation. Usually on the AP exam, from my research, we're often given a rate or a definite integral, and you're asked to find the total amount or a function value. This whole boils down to accumulation, and it's based on the fundamental idea of what calculus is about. Okay, so if you recall, basically from the proof of the video, if you take a derivative of an integral, you get the function back. So if I have a function f of t dt, and I'm examining it on this interval from just a variable to a constant, basically the whole idea is that the derivative and the integral cancel out, and you're just left with the function with the value of x plugged in. Well, that's the basic idea of what calculus is about. Now, there is a slight corollary. So this is kind of like the fundamental theorem of calculus. So basically, we have a derivative and an integral. So those basically cancel each other out. And I'm left with the value at b, subtract the value at a. And again, we'll go over this more in later videos. But for right now, I just want to show this, and we'll go over this and prove this later, because this whole idea is based off Riemann sums and accumulation. If I solve this to the other side, and if I get a to the other side, what I have is that this function b, or the ending value, is basically the starting value plus the area under the curve. And so what this says is really this value right here is the starting value plus your area that you accumulated. And right, so like we have the final amount, which is this amount, which is the initial amount plus the integral of the rate, or the net change in area. And so we're going to use this to kind of approximate some values. And we're going to use, this is going to be a calculator problem. So usually we're going to have some contextual problems, but before that, let's just practice this idea, this whole accumulation model. And so example 1 says we're given a derivative, and the derivative is sine squared of 3x minus 7. And we know that the function value at 5 is equal to 9. We want to find the value at 8. So let's write this as an integral. So basically we want to find the value at 8. We know the value at 5. And we have that this is a rate. Now we know that this cancels out, and that it equals the value at b minus the value of a, or the value of 8 minus the value of 5. And so we can write this as the value at 8 minus the value at 5. And when I say the value, I mean the function's value. Now we're given that this equals 9 from here. And so we're trying to find this. Now we're going to use our calculator for this part. So if I solve this and get this by itself, I'm going to basically add f of 5 to this side. So again, I wrote this as f of 8 minus f of 5. We know that this is equal 9. We added 9 to this side over here. And so basically we need to find this in our calculator. Now we know our function, and we don't know how to do this yet, but we can use our calculator to find this value on the calculator. And then for every other problem, I'm just going to type in the answer and assume that you could copy this process. So I'm going to graph. So this is my function, sine squared of 3x minus 7. And I want to find the area under the curve. of sine squared of 3x minus 7 from 8 to 5. When you have your calculator, type in your function here. And if I graph this, so basically I want to find the area under the curve from 5 to 8. So let's adjust our window so we can kind of see the function, but just in the area from 5 to 8. So if I go to window, I'm going to adjust my x values from 4 to 9, and then I'm going to hit graph. And so now I want to find the area under the curve. There are two ways to do this. So from here, I can either go to second trace, which is calculate. And then if you look at number 7, it does say the integral. So let's hit number 7. And so I want my lower bound. And again, I'm going from 5 to 8, so my lower bound is going to be 5. So if I type in 5, hit enter, and then it asks me for my right bound. And if I type in 8, hit enter, the function jumps over there. And if I hit enter again, so that is the area under the curve from 5 to 8. And if you could see, it does say it's 1.43192. And then if I add those two values, I'm going to get that my final value is 10.4319, and that was my value at 8. Again, because the fundamental theorem of calculus, if you take the integral of a derivative, you're left with the function at 8 minus the value at 5. There is a second way to do this. And so again, just remember that 1.43192. If I go back to my calculator here, if I hit math, notice that number 9 says function integral. So if I click on 9, it gives me the boundaries. So my boundaries are from 8 to 5. And then I can just type in the function here. And then I think on your calculator, you have to type in the x part so it knows that it's taking the derivative with respect to x. If I hit enter, oh, this is supposed to be, sorry, this is supposed to be minus 7, not plus 7. I get 1.43192. So you could take the derivatives on your calculator at values. And so that's my first value. Now, but all of these are just repeated. So again, if I want to find the value at 1, I'm going to take the integral from 1 to 5, because we know our value of 5, so that's a fixed value. And so again, from the fundamental theory of calculus, or a corollary of it, basically this integral is going to cancel with this derivative. I'm just left with the function at 5, subtract the value at 1. And again, I'm adding this to this side, and then I'm just going to subtract this off from this side and this side. And so when I do this in my calculator, I'm going to get that this value equals 1.9415. And then if I subtract that from 9, I'm going to get that f of 1 is equal to 7.0584. Part C. So to find f of negative 3, I'm going to go from negative 3 to 5. That's going to be basically f of 5 minus f of negative 3. We know that this is 9. So if I'm trying to find this, I'm going to add f of negative 3 to this side. So it's positive. And then I'm going to subtract this function over here. When I do this area in my calculator, I'm going to get that it's 3.9780. And then when I subtract that from 9, I'm going to get 5.0219. Moving on to example 2. So we have an integral, we have g of x instead of g prime of x, like the function. And again, just know that g versus capital G, one is the derivative, one is the antiderivative. So that's the derivative, that's the integral. So when we do capital, we're talking about the area function. When we're talking about lowercase, that's the derivative or original function. So we're looking for the area model. It's still the same principle. So let's write this out. We have the integral from 4 to negative 3 of g of x dx. Now again, when I do the integral here, I'm going to get capital G. So I'm going to get capital G of 4 minus G of negative 3. And again, this just means the area. This means the function. So we're taking the integral of the function to find the area. That's what the capital G means. Again, we'll go over this more in the next video. We know that this G of 3 equals 6 given in the problem. So if we're trying to find this, we're just going to add 6 to each side. Okay, and so we're going to do this function in the calculator. Now, be careful with this. This does say log, and then there's an absolute value here. If you do not type in this absolute value, you're going to get an error because you're going to get an undefined integral. So make sure you type in the absolute value, and I'll show you here on the calculator. So if you go to your calculator, you type in y equals. So we do need to hit the log first, so ln. Now, the absolute value is under math. And if you go over to number, you see how it says ABS? That means absolute value. And it puts the brackets in for you. So you just have to type in your function. And if you hit graph, and again, these little like humps that go down would go down to negative infinity. And that's why you would have an undefined area. But if you go to calculate, go to your derivative again. If you type in your left bound of negative 3, hit enter, type in your right bound of 4, and we get that the area is 6.18415. That's equal to 12.184, and that's what G of 4 equals. And again, you do have to make sure you type in absolute value. Let's do it the other way, just to show you one more time. If you go to math, hit number 9, which is the derivative function. Type in your boundaries. Always start with your lower one on the bottom. Now, again, we need to hit log. And then if you go to math, go over, there's the absolute value. And then type in x squared plus 3x plus 2. And then on your calculator, you'll have to hit dx. If you hit enter, you get the 6.18 for whatever. Next one, g of 0. So we're going to do the integral. We have negative 3 to 0. Again, this is going to equal g of 0 minus g of negative 3. And if we're trying to find g of 0, we're going to add the 6 to each side because we know that g of negative 3 is 6. And again, if we type this into our calculator, you should already have the value in. You're going to see that that equals negative 3.2273. And then my final value is 2.7726, and that's what g of 0 equals. Part C, so the integral, we're going to go from negative 7 to negative 3. Again, we're going to do capital g of negative 3 minus g of negative 7. We know that this value is 6. So we're going to subtract this to this side. So there's going to be a negative out front when we subtract it over. And then we're going to add this to this side. So we're going to get g of negative 7 equals 6 minus the integral from negative 9 to negative 3 of g of x dx. And when you type this into your calculator, you're going to get that it equals 9.4114. And then if you subtract those values, you're going to get 3.4114. And there you go. So it's practice using the area accumulation model and your calculator to find these values. So moving on, these questions are actually easier than the previous ones. It's using a graph to figure it out. So it does say that we're given the derivative of the graph, not the function. We know that the value at 0 is equal to 4. We want to find f of 5 and f of 3. So again, using the area model. So for part 1, we're going to start at 0 because we're given that value. And we want to find 5. And we want to find the area under the curve. Notice we are given the derivative. So basically, it's just this derivative and the integral cancel out. And we just have f5 minus f0. We know that f0 is 4. So we just need to find the derivative at 5 to find our answer. So I'm going to add 4 to this side. And that should give me my value at 5. Now, what is the area under the curve from 0 to 5? Well, that's just finding the area of this triangle here. Now, the area of a triangle is equal to 1/2 base times height. And so I know my base is 5 and my height is 4. And you got to have that. And so this is equal to 10 plus 4. So this value equals 14. Doing something similar for f prime of, or f of 3. So we're going to take, again, our integral from 0 to 3. We know that this is going to be f of 3 minus f of 0. We know f of 0 is 4. So if we add that to each side, we just need to find this area again. Now, the area under the curve from 0 to 3, so that's from here to here. Now, this is a trapezoid. You have that your first base is equal to 4. Your base 2 is equal to 2. Your height is 3. So this is going to be 1/2. 4 plus 2 times 3. I'm sorry, that is not exactly the value. It's not equal to 2. I'm sorry, did a slight miscalculation. So this equation is going to be y equals, again, mx plus b. So my slope is -4/5 x, and my y-intercept is 4. So now if I plug in 3 here, I'm going to get that it's -12/5 plus 4, which is technically 1.6. And so if I do this new area, I'm going to get 5.6 divided by 2, which is 2.8 times 3 plus 4. And that's going to give me an area of approximately 12.4. And that's what f of 3 is. So moving on to question B. We know that f of 5 is -1, and we want to find f of 0. So if we do our integral, this is going to be from 0 to 5 of f prime of x dx. So this is going to equal f of 5 minus f of 0. Now we know f of 5 is -1. So if we're looking for f prime of 0, we're going to add f of 0 to this side and subtract the integral to the other side. And again, we know that that is -1. So let's figure out this integral from 0 to 5. So that is a triangle. And we're going to have base times height divided by 2. The base is going to be 5, and the height is 4. And this is going to be 20 divided by 2, which is 10. So my final answer is going to be -1 minus 10, which is -11. That's what f prime of 0 is. So to find f of 2, we're going to go from 2 to 5. So this is going to be f of 5 minus f of 2. We know f of 5 is -1. So if we're trying to find f of 2, add it over, subtract the integral over. I know f of 5 is -1. And now to find this integral, we're looking from 2 to 5. So 2 to 5 is a triangle. We have our base, and that's equal to 3. Our height, again, looking at this equation, if I plug in 2 into here, I'm going to get -8 over 5 plus 4, which is approximately 2.4. So that's my height of my triangle. And again, this will be 1/2 times 1.4, which is 1.2 times 3, which is 3.6 minus 1. And so I get that the value is -4.6. That's what f of 2 equals. All right, last question, A and B. So given it's kind of the same thing, you just have a composition of shapes. And so it kind of gives you a description here of what everything is. It says given that the value is at 2, find g of 12 and g of -1. Again, it's still the fundamental theorem of calculus. G of 12, we're going to start out with 2, g of 2. So we're integral from 2 all the way up to 12 of g of x dx. We know that this is going to be, and again, this is not a derivative, this is the original function. So this is going to be an area at 12 minus the area at 2. We know that this part is 0. So this really is, we just need to calculate the area from 2 to 12. So from 2 is here all the way to 12. So we have this semicircle here. We have this triangle here. And then we have this rectangle here that we need to calculate. Now, remember, these are negative areas. This is and then what's above the x-axis is positive. So the area of a circle is pi r squared. Our r is going to be equal to 2. So we're going to have pi times 2 squared. But again, this is under the x-axis, so this is negative. Plus, we have our area of our triangle, which is 1/2 base times height. My base is 2. My height is 2. And then we're going to subtract our rectangle. Rectangle is base times width. So that's 2 times 4. Now, if we calculate all of this, this is going to be -4 pi plus 2 minus 8. -2 pi plus 2 minus 8. So this is going to be -2 pi minus 6 is what g of 12 equals. Our next value is going from -1 to 2. So this is going to equal the area from 2. Subtract the area from 1. We're going to use capital G. And again, this is lowercase g. If you take the integral, it's going to be the area, capital G. Now, we know this part is 0. So this is just equal to g of -1. So my area is basically equal to negative of g of 1. So we can technically switch the negative over here. Now, finding the area from -1 to 2. -1 to 2 is just this triangle. And again, that is half the base times the height. Now, since we are under the x-axis, it's negative. So we have -1, 2, 3. That's the base. And the height is 2. And so this is going to be positive 6. And that is my area. Oops, sorry. Times a half. I forgot the half. So it's actually 3. I forgot that it's half base times height. I just did the base times height. All right, last question. So we're given that g of negative 3 is 5. So we're trying to find these two values. So let's do negative 5 first. So we're going to go from negative 5 to negative 3. Again, taking the integral of the function just means the area from negative 3. Subtract the area from negative 5. We know that this value is 5 given in the function right here. And so if we're trying to find this value, we'll add it to this side, and then we'll subtract that value from this side. And so we just need to find the area from negative 3 to 5, or negative 3 to negative 5. So that is just this area here. It is a positive area. And again, that is going to be 1/2 base, which is 2, times the height, which is 2. So this is going to be 5 minus, and again, 1/2 times 4 is 2. So this value is 3. So the value here. So now we're going to go from negative 3 to 4. This is going to be g of 4 minus g of negative 3. We know that this is equal to 5. So if I just add 5 to each side, I'm going to get 5 plus the integral from negative 3 to 4 of g of x dx is equal to the area of 4. And so we just need to calculate this area from negative 3 to 4. So negative 3 to 4 is going to be comprised of this triangle and this quarter circle. So this triangle, again, this is under the x-axis, so this is negative. So the base is going to be, what is that, 1, 2, 3, 4, 5. So negative 5 and then 2. So 1/2 times 5 times 2. And it's negative because it is under the x-axis. So this is going to be negative 5. Plus, we're going to have the quarter circle. So again, that's going to be a quarter of a circle, which is pi r squared. My radius of the circle is going to be 2. So this is going to all be 1/4 times 4, which is 1. So it's pi. So this is going to be 5 plus negative 5 plus pi. And that gives me that it is, oh, and I'm sorry, I forgot, since this is under, this is going to be negative. So that's going to be 5 plus negative 5 plus negative pi. So it's negative pi is what your g of 4 is.